So just now we learned about the goodness of fit. So we want to test whether the frequency, okay, of your category follows certain theoretical distribution. So whether the frequency is fit, okay, to a theoretical distribution. So now we move to the next one. So the chi-square analysis of contingency table. So sometimes the question that we ask is not about the differences in the frequency, but we want to know if there any association, okay, any relationship between the category in terms of their frequency. Okay. So in this case, we collect usually two variables, okay, at the same time. This is an example that I showed you earlier. Okay. So the purpose of this test is to test the hypothesis that the frequency of occurrence in the various category of one variable are independent of the frequency of the second variable. Okay. So the variables is this, okay, or you might say factor depend. Okay. Whether a student wearing glasses or not depend on the gender. So is there more male student wearing glasses than female student? Or there's no difference, there's no association. Okay. If there are more male students wearing glasses compared to female student, okay, so that means that whether a student wearing glasses or not depend on the gender. Okay, it's not independent. So there must be some association. Okay. So this is, for example, this is after you summarize data, this is how data look like. Okay. So just look at this data. You don't really know whether there's a association or no association. Okay. So this is what you observe. Just like the goodness of fit, you need to calculate or hypothesize what you expected. Okay. So this is what you expected, what you observe. Okay. And this is what you expected. Okay. So this is what you observe. You only have this data after you have done your sampling. Okay. But what you expected, you should have this one even before you conduct your sampling. Okay. Right after you have your research question, then you should have the frequency of what you have expected. Okay. Again, this is a sample size of 20 collected from a large population. Let's say a population of 10,000 students. Okay. Now you have 20 students. Okay. And you know that in that population, there are 50% male student and 50% female student, let's say. And you also know there's 15% of the student with glasses, 15% of the student without glasses, out of the 20. Okay. So if there's no association, what are those value or frequency for each category that you observe, that you expected? So you can calculate this way, because the total is 20, okay, and half of the 20 with glasses, another half without glasses, correct? So that means that for the male student, if they follow the general trend, then you expect that there will be 5 with glasses, 5 without glasses. Okay, same as a female student, 5, 5. Okay. What if the population is not homogeneous? So I do some sampling before I collect, set some criteria when I do the sampling. So let's say the male is 20, so the total is 30. Okay. And the student with glasses and without glasses is 15, is 50%, 50%. Okay. So now, if I ask you, from the expected frequency, okay, based on this data set, okay, based on your hypothesis, how many male with glasses and how many male without glasses? Okay, this is 10, 10, right? Because half of them with glasses, half of them with the glasses. How about this one? Okay, same as this one, 5, 5. Okay. You can see this way or can see another way. Okay, you know that there are 15 students with glasses, and 2/3 of these students are male students. So 10 of them should be the male student, 5 of them should be the female student. It's the same thing. Okay, so this is how you can calculate the expected frequency. So just now you have figured it out. Okay, this is the expected frequency. So you know that if you just look at the number, you know that there are some differences. So the next question is whether the differences is significant. Okay. So we use the exactly same formula to calculate. So you just calculate the difference between the observed minus expected, square it, then divide by what you expected for the first category. Then do the second one, to the third one, to the fourth one. Sum them up, then you will get the chi value. Okay. In some other textbook, you might see other type of the formula. Okay, but what they calculate is very similar. Okay, you might see this formula, but they are same things. Should not worry too much. But we will not discuss this in detail because if I start with this formula, you don't really understand the concept. Because for this one, if you observe, they don't really deal with the expected frequency. What you need to put in is just the first observed value, so f11, f21, multiply them minus by f12, f21, okay, then square it, multiply by the n is 20, divide by the sum of the first category, second category for the row, and also the column first category, second category. That's all. Okay. So from the calculation point of view, this formula is easier. You just take the value and plug in. You don't have to calculate the expected frequency. But we will not use this for this course. Okay. Mathematically speaking, they are the same. Okay. This is just a shortcut. And sometimes you will see something like this. Okay, it's more complicated. Even the chi-square, you can find a whole chapter to discuss different variants of the chi-square. Okay, but we will not discuss in detail. If you want to learn more, after you understand the concept of the chi-square, you always can refer to those books. Okay. So this is my research questions. Wearing glasses is independent of gender. This one. Okay. So you just look at the value without calculate the expected frequency, or you might calculate it in your heart. You know that there is no, it's not significant, right? So it's independent. Okay, whether the student wearing glass or no glass is independent. This one is not independent. You can see all the students with glasses are the male student. All the students without glasses are female student. You just notice the difference. The total is the same, right? The total for each category also the same. Okay. So for this one, then the answer will be no. For this one is yes. For this one is no. Not independent. So this is quite straightforward. How about this one? This one? So it's very hard to say, right? It's quite subjective. If you just based on your judgment, so you want to do some objective analysis. Okay. So the analysis that you want to use is a 2x2 contingency table. So I show you the simple version of the contingency table, the analysis of contingency table. So the table can be 3x4. Okay, it can be 3x4 by 2 by 1. Okay? It can be very, very complicated. Okay, depend on your research questions. So the one that I show you is that we're going to discuss is in detail is 2x2. Okay. So this is a formula. So it's actually it's the same formula. Okay. So if you calculate this, you just make a table. Okay, you just calculate the observed. You just take the observed value, put in one column, then calculate the expected value, and then calculate the difference between the observed and the expected frequency, square it, divide by the expected frequency for each category. Then after that, you sum them up. Okay, sum all the value. So first, formulate a hypothesis. So the hypothesis is something like this. So for this test, you should test the relationship. So relationship means whether these two variables are independent or not independent. Okay, from each other. Okay, so but we will not say the relationship, but we will test the independency. Okay, or association. After that, you need to set the criteria. So this is exactly same how you can find the criteria, the critical chi-value for your goodness of fit. The only difference now is, just now for the degree of freedom, you have only one category, right? Okay? And sorry, you only have one variable, two category. So you take a number of the category, 2 minus 1, you get the V equal to 1. In this case, you have two variables, and each variable have two categories. Okay. So what you can do to calculate the V is to take the total number of the first category, total number of the category for the first variable minus 1, total number of the category for the second variable minus 1. After that, multiply these two values, not plus, multiply. Okay. So this is 2. 2 minus 1 is 1 for the row. For the second variable is 2 category, 1, 2, minus 1 is 1. So 1 multiplied by 1 is equal to, so this is 1, 2 minus 1 multiplied by 2 minus 1. So it's 1, 1 that is equal to 1. So your degree of freedom is a 1. Okay. Then you refer to your table, check the critical chi value, which is correspond to your alpha and also the degree of freedom. Okay. Then you get your critical chi. Then after that, you can do the test. Okay, calculate the statistic. Okay. So after you calculate the statistic, then you can compare your critical value with the calculated value. So this is what you calculated, 3.200. This is the critical value. Okay. So this calculated value is smaller than 3.841. So you will not reject the null hypothesis. So that means that these two variables are independent. Okay. So you just compare them, you get the answer. So that's all for the chi-square contingency table.